Hello, everyone, and thank you, Charlene, for inviting me. I share the screen now. Okay. Right. Okay. You can see it, right?
Yes, we can.
Yes.
Thank you. So yeah, I'm a postdoctoral fellow at KTH Royal Institute of Technology and Silent Lab at Stockholm. And when I joined GROMACS team a year and a half ago, I started working on adding oneAPI support to GROMACS. GROMACS is a multi-dynamics engine. It's one of the most widely used HPC codes in the world, and by some estimates, it accounts for around 5% of supercomputer usage in the whole world. And GROMACS runs not only on supercomputers, it's also part of Folding at Home, which is run on laptops of volunteers all over the world. It's run on desktops. GROMACS also, of course, is run by individual researchers on their workstations. So it does support a huge range of hardware and a huge range of the system it's modeling. Sometimes we can model efficiently tens of thousands of atoms, like individual proteins, or a whole protein complex embedded in membranes, which will over 1 million atoms. So it's several order of magnitude in terms of what we are simulating and in terms of what hardware we have. And besides just a huge range in terms of flops, we also support multiple different hardware architectures. It's most modern CPU architectures. We have manually tuned SIMD kernels for different instruction sets. We have capability to offload to most modern GPUs as well as the on-PHY. And while most GROMACS development happens and is targeting Linux, we also support Windows and macOS. Also, your mileage may vary about how well it works. So I said Linux is our main platform. Looking at the most recent release, which was published in late February, GROMACS contains around 500,000 of C++ lines code. It's mostly modern C++ 17 standard compliant code base, but since our code has around 30 years of history, of course, there is legacy bits here and there. And to be able to scale to such a wide range of hardware, we support multiple layers of parallelism. We use MPI for parallelism between different nodes in the cluster. We use OpenMP for multi-threaded parallelism within a single node. For low latency operations on CPU, as I said, we have SIMD backend tuned for different SIMD instruction sets on both x86 and Spark and ARM. And for high throughput operations, we have in GROMACS 2022 3 different backends. We have CUDA for offloading to NVIDIA GPUs. We have OpenCL that also supports NVIDIA GPUs, but is mostly a compatibility layer, and it's used for AMD and Intel. And recently we added SYCL, which currently can target also all 3 main vendors. Also, NVIDIA is for us mostly an attempt to keep the code compatible. For NVIDIA device, we still recommend at the moment CUDA. Now, what exactly are we accelerating? So, okay, we have all this multi-level parallelism scheme. What are we applying? Microdynamics is very similar to a well-known n-body problem, except we have more complicated forces involved. So we have multiple particles, there are forces acting between them, and we compute forces acting on each particle, integrate its movement, rinse, and repeat. And repeat we must many times, because one time step of microdynamics in full atom mode is around 1 femtosecond, sometimes up to 4, but on that order of magnitude. But we need to simulate, if we want to capture any biologically relevant processes, around several microseconds or even milliseconds. So it's billions of steps. And that's why we need to run this loop of force computation and integration very, very fast. And to achieve that, we have several goals that are sometimes at odds. We need to minimize latency and be able to submit the workload to GPU as fast as possible. And we also want to minimize stalling on either CPU or GPU, because, well, if it can do work, then it probably should do work and reduce the bottleneck on the other device. And of course, we need to minimize data exchanges. So while we want to balance the use of CPU and GPU, we don't want to, we still need to split the workload and avoid transferring data too often to avoid hitting the PCI Express bottleneck. And of course, if we are running on a cluster with multiple nodes, we do want to keep the data exchange between nodes to a minimum and try to optimize it so it doesn't become a bottleneck. And that's already not too easy, but additionally, since GROMACS runs on wide range of hardware and wide range of simulated systems, the optimal scheme to offload hugely depends. Whether we are simulating 10,000 atoms, it might be faster, 1,000 atoms might be faster on CPU to avoid hitting the data exchange bottleneck. If we are running a huge system, probably we will benefit from using multiple GPUs. Additionally, we want our code to be fast, but we also want to keep it relatively simple to be able to actually maintain it and develop it. So that's a tricky balance to keep. And because of this, the real schedule, the real workload schedule looks like this. It's one of the possible schedules because GROMACS can support different operations on either CPU or GPU, depending on the specific of the hardware. For example, we might have multiple CPU cores per GPU, or we have many, for example, powerful A100 NVIDIA GPUs for 2 relatively low core count processors. So it depends on what hardware you have and what are you simulating, which operations you want to have on CPU or GPU. We do have some tuned framework, mostly related to the pair list size and pair list buffer, which can somewhat balance the workloads between CPU and GPU and either increase the frequency of required pair list update or increase the, which improves the performance. Or if we have more frequent updates, it will, on the other hand, offer faster force computation. So there are a lot of variables at play here, and even while we try to keep things simple, our force schedule and the number of the modes which we support, it's pretty complicated. And in GROMACS 2020, which was released in January of that year, we only supported NVIDIA and NVIDIA CUDA and OpenCL for offload. So we had CUDA as the most mature and most feature-rich backend, but it was only able, of course, to target NVIDIA GPUs. And as compatibility layer, we were using OpenCL. It had less feature supported. It wasn't able to offload as many operations as we could with CUDA, but it allowed us to run on AMD and Intel devices, which was at the time considered acceptable. So we had most of our efforts, of GROMACS team efforts, spent on CUDA, with OpenCL being supported to some extent. Let's put like this. But nowadays the landscape is changing. We are having new modern exascale systems coming in initially 2021, but now hopefully this year. We have a huge Loom machine that's not exascale, but still one of the primary targets for GROMACS. And all those machines, they're not using NVIDIA GPUs, they're using either AMD or Intel. So we had to change our approach. So it's not CUDA first anymore. We need to put more efforts into supporting other vendors. And of course, first you might think that we had OpenCL, maybe we should develop that. The problem is that OpenCL is not too great. As I mentioned, our code base is C++17, while widely supported OpenCL implementations, especially at the early 2020, only handled C99. So we had to duplicate a lot of code and repeat structure declarations, etc., to have it both with C++ and with C. And this separate source model is also not very convenient for development. Also, OpenCL uses its own syntax, so all the formatting tools, all the linters, we don't have them working nicely with OpenCL code. So that makes OpenCL technically viable solution, but it's a huge maintenance burden. And compared to that, we have SYCL, which is an open standard like OpenCL, so it's not proprietary vendor locked one like CUDA. Another benefit is while SYCL is relatively new and still actively developed, it's not trying to reinvent the wheel. It's based on existing backends. For example, Intel's oneAPI supports OpenCL, and there is also a collaborative effort with between Intel and Coplay to support CUDA and AMD devices, again over CUDA and HIP backend. So it's not trying to reinvent the whole stack, only the programmer-faced parts. It's actually open standard in terms of there being other implementations. It's not just oneAPI. oneAPI is great, don't take me wrong, but we have actual other implementations that are actively developed, that are usable. So it's not a vendor lock. It's really portable open standard. And since it's built upon other tools, we can use existing profilers, debuggers, etc. to work through code. We don't need to wait for oneAPI specific or SYCL specific tools. We can use whatever we already have. And SYCL is built on standard C++. It doesn't use any custom syntax like this Chevron kernel launches. So all the existing IDs, linters, code formatters just work. And in terms of architecture, SYCL is inspired by OpenCL. And if you have OpenCL code, you don't need to re-engineer it from ground up to support SYCL. In most cases, you will need to do some rewrite, but you don't need to change the whole logic of how your application is structured. So yes, that's current state of GPU frameworks, at least the way it's relevant to GROMACS. So SYCL is not as mature as either CUDA or OpenCL, and officially it's only supported by Intel as a vendor, but there are functional and pretty stable support for devices by other vendors. It is nice single source model and modern C++ 17 syntax without any additions. We did that support for some very minor SYCL offload capabilities in GROMACS 2021. And in 2022, while it's still experimental because it's the first GROMACS release supporting SYCL, so we do say that it's less tested and less proven than CUDA that has been over 10 years in GROMACS, but we do support most of the offload features, so it's a fully functional offloading framework for GROMACS now. And how did we get there? When the works only started in September 2020, we decided to focus on using Intel oneAPI, since it was the most developed and the most stable SYCL implementation at the moment. But we did want to stay standard compliant. GROMACS takes pride in being portable to multiple compilers, multiple hardware architectures. So keeping the code close to the SYCL standard and not relying all too much on vendors' extensions is a good way to continue this tradition. And first, we decided to do, of course, some device detection initialization and try to clean up the existing code to avoid CUDA or OpenCL bits that cannot be easily translated to SYCL. Then, of course, we decided to port the non-bonded kernel that in typical run account for most of the computational work. And then we want to port other kernels that allow us, for example, to fully offload the simulation to GPU to be able to run the whole MD loop, except the list updates on the GPU without any CPU work, which of course will completely resolve all the issues with data transfers. We first considered using the DPC Compatibility Tool that can transform CUDA code to SYCL. But the problem is that it's not that much of an effort to actually port the kernel. Of course, it's quite a bit of work, but it's relatively trivial. And the biggest problem is actually having a nice portable layer that allows us to have both CUDA, OpenCL, and SYCL together in the same code. We already had some abstraction layer for device, queues, contexts, device buffers for CUDA and OpenCL, so it makes more sense to work on expanding and developing this compatibility layer rather than trying to just do some conversion. And another thing is that we do have OpenCL kernels tuned for Intel and AMD. On the other hand, CUDA kernels are tuned for NVIDIA. They use 32-bit wide, 32-thread wide execution. They are tuned by for specific block sizes, grid size, block sizes to run well on NVIDIA, and that doesn't usually work well for Intel. So just porting NVIDIA optimized kernels to SYCL wasn't really all that useful for us. We weren't planning to get rid of CUDA, so running SYCL code on NVIDIA devices was nice to have, but not a primary goal. And thus, we concluded that using DPC compatibility tool wasn't really all that helpful to us. Again, depending on your project and goals, it might be useful. It might be useful for porting individual kernels, but for GROMACS, that was not the main concern. Besides we started porting, we had to consider what SYCL standard to use. Now, at the moment, September 2020, we only had SYCL 1.2.1 standardized. SYCL 2020 was just a draft. But unless we wanted to get rid of all the optimizations we had in our OpenCL kernels, like shuffles, atomics, etc., we couldn't just settle with using SYCL 1.2.1. So we say that while it's nice and good goal to be standard compliant, we had to use the not yet published and not yet settled SYCL 2020 draft to do the work. And we also had to rely on some oneAPI extensions, although most of them indeed became part of the standard, so that was a nice compromise to stay as standard compliant as possible without sacrificing the performance. We look at how the GPU frameworks are structured. In CUDA, we have as a primary method for organizing GPU work that's in order queue. There's also support for explicit graphs, CUDA graphs, but we are not using them currently in GROMACS. OpenCL supports both in-order and out-of-order queues, but in GROMACS we were, of course, to minimize the divergence from CUDA, we're relying on in-order queues. And here comes the problem with SYCL, because in SYCL, at least in the 2020 standard, there were no in-order queues. The primary way for submitting work to the device was implicit data access graph. Another difference is the synchronization, because in CUDA, the event is something that you put in a queue and it acts like a barrier. Now, in OpenCL, event is usually something associated with a task. You submit a task, you get an event associated with it. You can also submit a barrier, but to stay CUDA compatible. And that's actually what we were doing, again, to minimize divergence. But with SYCL, there is no standard compliant way, not in SYCL 1.2 nor in SYCL 2020, to just submit a barrier. We only have events associated with specific tasks. For timings, again, it comes from the way synchronization is handled. In CUDA, you measure time between two different events. In OpenCL, you measure time of a task associated with this event. But for that, as well as the way timing, enablement, and device selection is handled, we already had an abstraction layer. So we already had our code engineered, sometimes a bit cludgily, in a way that we can handle timings in both for both the region approach and for both single event approach. We also had nice compatibility layer for device selection, for controlling whether you want to enable or not the timings. So a lot of things we already had abstracted away nicely, and since SYCL was following the logical concept there, it was not important concern. Now the scheduling. That is handled differently in SYCL and OpenCL. So we had to actually do some research and make some hard decisions. In theory, DAG-based scheduling is really good. It prevents any concurrency bugs by ensuring that all the tasks run in parallel, and automatically by specifying which data is needed where, you ensure there are no data races or other things. It should improve performance by automatically enqueuing kernels that can run in parallel to run actually in parallel. So it sounds great. And if we were dealing with new code, it actually could have been very nice to have it. It simplifies a lot of things. The problem is that GROMACS, all those problems have already been solved. We already have multiple in-order queues. We already have a schedule that splits the work between them. We already have explicit barriers to synchronize, which can lead to either having a bit of an overhead because we have both synchronization from DAG and our manual synchronizations. And besides, there is a possible issue when doing the host copies, device to host copies. Because if we submit multiple operations and then an event to an in-order queue and then wait for this event, we can be sure that both operations are completed. Now, if we have DAG and we get the event from the second operation and we wait for its completion, we can know that the second operation has completed, but we don't know anything about all the previous ones. So when trying to shoehorn DAG scheduling and in-order queues in the same code, such implicit dependencies can be a problem. And another concern is that while we have our code optimized for CUDA, that puts for in-order queues, that actually puts a lot of strain on how well the scheduling by the SYCL runtime is handled. Because we did a lot of manual tuning, and it's not guaranteed that automatic and pretty new and not very well field tested, so to say, runtime will do as good job. For example, we have this critical path shown in red arrow here that processes the atoms that are shared with neighbor in ranks, and we want it to complete as fast as possible, so we don't stall neighbor ranks. So we compute the work, the force that should be sent to other MPI ranks as soon as possible, so we don't have make those ranks wait for us. And in SYCL, there are no explicit way to put priorities, nor way to say that this path through graph is critical, so it should be prioritized when scheduling work. There is just no way to express that. With in-order queues, it's also a bit awkward, but yes, you can just enqueue work earlier, and that usually does the trick. But with DAG, which can rearrange the workloads more or less freely, there are no guarantees that the work we consider high priority will actually be executed as such. And besides having in-order queues for some backends and DAG-based approach for SYCL, honestly, that increases maintenance burden. We are not a big team, so we cannot support two completely different scheduling approach. Now, unfortunately, in late 2020, USM and in-order queues were not yet standardized. So as an initial approach trying to be standard compliant, we were using SYCL buffers, but we're treating them like a simple device memory with explicit copies to existing host buffers and explicit synchronizing on those copies. We experimented with trying to avoid explicit synchronization between device work, but honestly didn't show any improvements compared to our manual synchronization. So yeah, I guess we can say our schedule is indeed close to optimal, at least. Yeah, the runtime couldn't figure any better way to arrange the GPU work And in 2021, when SYCL 2020 was finally released, standardized, and supported by existing implementations, we switched to using USM and in-order queues. Also, we are still kept buffers as an option. And another reason was that for some compilers, specifically, first we experienced it with AMD, but also for some versions of Intel devices, using accessors in already complicated kernel was too demanding for the compiler and it wasn't able to optimize them nicely. We had register spilling, we had performance problems with accessors, but just passing USM pointers, that's easy. Pointer is not some complicated data structure. It has no range, it has no size, it has no nothing. It's just a pointer, so it doesn't use extra registers. It's really easy to optimize, and it doesn't require the compiler to do the impossible. Another issue is the, as I mentioned, synchronization, because there is no standard compliant way to associate, to submit a barrier into the queue. We only can wait for specific tasks, and that can lead to synchronization problems. Unfortunately, we haven't found a beautiful solution here. We had to rely on the custom extensions, specifically oneAPI and queue barrier extension from Intel's oneAPI. That does exactly that. It just includes a barrier, and when we wait for this barrier, we can be sure that all the previous submit work is complete. And speaking of other implementations, we did talk with hipSYCL team with XLPy, and he helped us by adding the somewhat similar extension to hipSYCL, also allowing us to wait for all the previous submitted work. So for that, there is no yet a standard compliant way, but there are workarounds. And those other differences between backends, as I said, they're already handled. Our team spent a lot of effort on unifying code to handle both CUDA and OpenCL. So when SYCL came and in aspects where it was similar to OpenCL, we could just use the same logic behind this OpenCL and avoid any hassle. Other major differences that I guess should be considered when porting is slightly different handling of errors. We don't have error return code like in CUDA and OpenCL. We have exceptions. Not a big deal, just something to keep in mind. Also, if you're coming from NVIDIA only or from AMD only, there you have fixed subgroup size, 32 or 64. For Intel devices, the SIMD width can be varied, and usually for the current generation of GPUs, 32 is not optimal unless we are talking about really simple kernels. Another thing that beat us several times when doing the manual porting of the kernels is the thread ordering, because in CUDA and OpenCL, the first dimension, if you have multi-dimensional grid, is the fastest changing. In SYCL, on the other hand, it's the last dimension. So if you have a multi-dimensional grid and some, say, warp level operations, subgroup level shuffles, etc., then this is something you need to always keep in mind. Now, that's about porting the code to SYCL. And when I say SYCL, I indeed try to keep things standardized and not limit the discussion to oneAPI. Again, oneAPI was our primary goal when doing the port, and it is one of the main backends we do support. But we do try to use to make it, not another vendor-specific backend like CUDA. We want to keep it standardized, and the only way to keep it portable. And the only way to ensure that we are actually in practice portable and not just we should be portable, we need to use other backends just to verify that our code works. And besides, as I said, one of the targets for SYCL as a compatibility layer is AMD devices. And currently, DPC++ does not support them, although there is ongoing work by CodePlay to add the support to the code base. And we decided to use hipSYCL, which at the moment was very well established already. And it did support, well, hip AMD devices through the ROCm backends. And also it had CUDA support, which is nice to have. It won't hurt. So yeah, we started with code that was targeted at oneAPI and Intel devices. And later, several months after, half a year almost after the development started, we added hipSYCL to target AMD devices. And in terms of how well it went, I can say it went pretty smoothly. We had to work around some backend and compiler issues, particularly because different parts of the standard were implemented, like some parts were implemented in SYCL namespace and in oneAPI, in hipSYCL, and in oneAPI it was in the Ext1API namespace. In hipSYCL there were no support for subbuffers, but they were not crucial. The big thing was the enqueue barrier extension. And for that, we had to work with hipSYCL team to find a solution to add another extension that allowed to have similar workflow. There were some bugs that, like our code was incorrect in some places, but it wasn't actually leading to incorrect results with oneAPI, but it was getting triggered by hipSYCL. So that's already a benefit. Using AMD devices and different backends allowed us to have a better code. We had to do quite a lot of CMake, not too much, but probably more than we wanted, of CMake coding to support both backends. And we already had more or less optimized kernels in OpenCL. So device optimizations were just moved from verbatim from OpenCL to SYCL. And that relatively low effort allows us to now, with GROMACS, target all three vendors. You can target Intel GPUs with oneAPI. We can target new AMD GPUs by hipSYCL, and hopefully with new release of ROCm, older GPUs will also be supported. They're promising it every release. They still haven't delivered, but we hope. And we support NVIDIA GPUs via both open source Intel LLVM, which is the basis of oneAPI, and via hipSYCL. Now, compared to the native performance on AMD devices, complex kernels are slower. They were much slower when we were using accessors. When we switched to USM and simplified the job of compiler, they became just quite slower, but not horribly slower. And for simple kernels, like our integrated kernels, the performance is usually similar to native hip or OpenCL code, sometimes even faster, although we are still encountering some runtime specific overhead. The runtime tries to be smart, tries to schedule work in a nice way, and it doesn't always work all that well. And we had very little actually code that's vendor specific. We had, of course, to change the code that uses warp level reductions, warp level shuffles, because the subgroup size are different on different hardware. And since we also use GPU FFT, we had to work a bit to support different FFT backends. For Intel GPUs, we obviously had to use oneMKL. It's great, it's nice, and it natively integrates with oneAPI. For AMD GPUs, we were using RockFFT via an extension of hipSYCL that allows also pretty nice interaction between native API and SYCL API. And the same can be done for QFFT and NVIDIA, but we haven't done that. As I said, NVIDIA is not a first priority target for our hipSYCL port, so yeah, we do ensure that it runs well, but so far we haven't ported the FFT invocation code yet. So that's in brief our journey of adding SYCL and what main challenges and problems we encountered. Other things worth noting. It's really great that we can use existing debugging tools. For example, NVIDIA Compute Sanitizer recently allowed us to find a bug in our kernels that actually was affecting not only CUDA devices, but also other backends. So it was a logical error in our code. And by being able to run it on NVIDIA and use this really mature and stable tool to debug issues, it really helped us to improve code for other backends as well. Another possible thing to know that is unlikely to affect other code base, but was and still kind of is a problem for us, is that compilation is pretty slow. For example, in one file, we have 168 different templated flavors of a single kernel. And it takes several minutes to compile. And what's worse, it was taking several minutes to compile even in runtime because the just-time compiler was doing its job on all 168 kernels, despite the fact that only 2 flavors usually are used, 2 or 4 flavors are usually used during the single round. So luckily, there is this helpful switch, fSYCL code split per kernel in oneAPI compiler that that tells just-time compiler to only work on kernels that are currently used and not try to compile all the kernels process all the kernels in that file. So again, it's probably not something many people will have trouble with, but if you have them, here's the solution. And of course, SYCL being a relatively young standard compared to OpenCL and CUDA, and the implementations being even younger, that's both a good and a bad thing. We have new and exciting features added, and it's possible to even influence the development of the standard. So that promises a bright future for it. But currently, things are in turmoil. And if you had written some code and it compiles and runs fine, in half a year, chances are with the most recent compiler, it will at least, it's very likely to at least emit a warning. It might even refuse to compile because some features were removed. Now, in most cases, they're not actually removed, they're just moved between different namespaces or renamed. So it's relatively easy to fix, but it adds this minor but constant maintenance requirements to keep things up to date. And of course, with new compiler and new runtime, there is always a chance that something will be not only deprecated or added, but also existing functionality might be broken. It happens, such is life, but yeah, it is adding some maintenance burdens that we have to keep in mind. And to have an overview of our porting effort, we started in September 2020 with me joining the team. And by January 2021, 4 months later, we did release a separate GROMACS version with basic offload support for Intel GPUs. 1 year later, in September 2021, we officially selected SYCL as a main way to support the future AMD GPUs, and specifically the Lumi machine. And in February 2022 now, SYCL is part of the main GROMACS release. It's fully functional, officially supported, offload backend, support which runs on all 3 main vendors and supports most of the GPU offload features. If in 2021 we only supported non-bonded forces and had some integration support, in 2022 we support most of the 2 biggest force calculation kernels, that's non-bonded and PME, and we support full integration pipeline, so we can run in fully offloaded mode in some cases. And in terms of what we can offload, now SYCL has even more, SYCL port has even more features than our OpenCL. It's still lagging behind CUDA port that is still actively developed and likely will be for the foreseeable future. But yeah, I would say SYCL now is close second. To conclude, the promise of SYCL as a portability layer and an open standard is mostly fulfilled. We wrote our code for oneAPI, and it was pretty easy to port it to hipSYCL, and probably if we decide to support another backend, it also won't be too big of an undertaking. If you want to get every single flop out of a device, you still need to tune for this specific GPU. If you have complicated kernels, compiler won't magically do its compiler won't do magic and optimize everything for every possible architecture. So you still need some vendor-specific, architecture-specific branching. But for simple kernels, usually the compiler is actually doing a decent job. And additionally, there are some current issues with runtime. We have some performance regressions with hipSYCL, but yeah, with oneAPI, usually the performance is pretty stable, except like with most recent release, we are having some troubles with level 0. But yeah, OpenCL works perfectly. It's stable, and running SYCL via OpenCL backend usually is currently the safest way. Level 0 sometimes it's faster, but also yeah, as a newer backend, it occasionally tends to be broken, but not too bad. And yeah, the API structure is very similar to OpenCL. So if you have OpenCL code, replacing OpenCL with SYCL should be pretty trivial. With CUDA, kind of depends. If you like us rely heavily on synchronization barriers and in-order queues, it might be more of a challenge. And besides, I want to say that yeah, it's what we have now, but SYCL is evolving very rapidly, and yeah, things change, and hopefully for the best. Now I would like to thank Intel for organizing this workshop and inviting me here and for offering me a scholarship to work on this project. I would like to thank Heinrich Bockhorst and Ron Schultz from Intel for their help with oneAPI and Intel devices. Axel Alpay from Heidelberg for his help with hipSYCL, and of course the rest of the GROMACS team, in particular Mark, Paul, Zillard, and Artem for their work. If you want to learn more, here's our website, our developers list. Our development happens on GitLab. It's fully in the open, so you can go and see and report bugs. Here is the most recent documentation, and here is the paper describing a bit more the algorithms used for GPU offloads that are mostly similar between NVIDIA OpenCL and between CUDA OpenCL and SYCL. Yeah, and if you have questions, feel free to reach out to me via this email. Thank you.
Wow, Andrey, thank you so much for